Okay, so we start now with Eucild. Thanks.
Thank you. I hope that you have all been afraid after coffee. And so I'll continue this morning's topic to talk about some dirty work connecting modified gravity theories to observations. And the topic here is the opposite of the first talk this morning, which was about weak-lancing peaks. Here I'm talking about weak-lancing valleys, which are caused by cosmic voids. If I finish this talk well in advance, I'll talk about something else quickly. So this is the brief outline of this talk. I'll first give a description of the context and motivation about cosmic voids and FFR gravity, and then I'll go to methodology, which covers the simulations, the galaxy catalogs, and the void finders used to find voids in this project. And in the third part, I'll talk about results related to void statistics, including void abundance and various profiles of voids. And there I will also talk about some forecast for Euclid and LSST surveys. And then I'll briefly mention constraints on other models. So voids are very familiar to all of us. These are low-density regions in the universe, and they occupy the majority of the space of the universe. So this is a plot showing the density map in a simulation box where bright color means high-density regions and dark color means low-density regions. And the circles are the voids found from this density field. So you can see that the voids covers low-density regions. And because void cover low-density regions, they are natural test beds of modified gravity, because many of these modified gravities have screening mechanisms which do not work in low-density regions. So there are various challenges in using voids to test gravity. So for example, voids are not regular shaped, and they can be defined in different ways. So there's a variety of ways you can define voids, and voids have many different properties. These void properties are also sensitive to different gravity models in different ways. And because of these complexities, we want to make a systematic study of the potential of using the various observational properties of voids defined in various ways to constrain various modified gravity models using data from various cosmological surveys. And this is the first part of this big project in which we focus on this simple FFR gravity model. And this model has been discussed several times in this workshop. And it is chosen because it's popular, because of its popularity, because it has rich phenomenology. It can cover the phenomenological predictions of many different classes of models, and also because it has the computational advantage, mainly in that nowadays full embodied simulations for this model can become fast. And this model, of course, is not a fundamental model. This is why we are not trying to use observations to constrain the function form of FFR. Instead, what we want to do is to say to which extent can current and future observations constrain chameleon-type deviations from GR. So the simulations used in this study are the so-called elephant simulations run using the Cosmological code. These are the simulation parameters and cosmological parameters. Most of them are not very relevant here. So what is relevant here is these two parameters, which are FFR gravity parameters, n, which is set to 1, and FR naught. We choose 3 different values. When it is 0, we get GR. And when it has values of 10 to the minus 6, we get a weak deviation from GR. And this model is called F6. And similarly, a model F5 has a deviation which is moderate from GR. And this is quantified by this number, 10 to the minus 5. And the box of the simulation is 1 gigaparsec. It contains 1024 cubic particles with a mass resolution of about 8 times 10 to the 10 solar mass. So most previous studies of voids using either voids found from the dark matter density field or voids found from the dark matter halo field. And in this study, we want to make a step further, and we want to find voids from galaxy field, and because galaxies are what we observe in galaxy surveys. So what we do is that we first identified dark matter halos from the simulations using a Rockstar halo finder, And then we populate these halos using the so-called halo occupancy distribution method, which is basically a phenomenological model to populate galaxies in dark matter halos. So what this model does is that for a given halo mass, it predicts the mean expected value of central galaxies, of number of central galaxies and satellite galaxies in this halo. And these are given by these two numbers. And then you draw random realizations to populate central galaxies and satellite galaxies in these dark matter halos. To make it close to observations, we have chosen the HOD parameters. There are 5 of them, which are these blue symbols. We choose these parameters for the GR simulation to match that from the Bose-CMAS work. And if we use the same HOD parameters in GR and in abstract gravity, then we will find different galaxy clustering properties, different galaxy number densities. This is because the halo number densities and halo clustering in these models are different. So observationally, we only have one universe. We only have one galaxy field. So what we do is that we assume that whatever gravity model it is, it predicts the galaxy field that we observe. So for that reason, we have tuned the 5 HOD parameters in the modified gravity model so that the different models all predict roughly the same galaxy number density and the same 2-point statistics of the galaxy field. So this is a result showing the galaxy clustering, 2-point galaxy clustering of the tuned galaxy mock catalogs. On the left, I'm showing the GR galaxy correlation function as the black line, while the different color lines are the F5 model galaxy clustering for different HOD tuning schemes. If we use the same HOD parameter as in GR, we get this blue line. As you can see that this galaxy clustering now is about 10% lower than in GR. And on the right, I'm showing the properly tuned HOD galaxy catalogs, for which you can see that the different color lines from different models and different redshifts all agree with GR very well. So as I said, there are different possible ways to define voids because voids are so complicated objects. Here in this project, we compared 6 different void finders. I'm not going to talk about the details of these void finders, but I want just to say that the top 3 are voids found from the 3D galaxy field. And the bottom 3 are voids found from the 2D projected galaxy field. You can see a common feature that all these void finders, they found low density regions because they coincide with dark regions of the density field. But they're also very different. You can see that even within the 3D void finder cases, if you use different void finders, you generally find different void populations. And this is especially true if you compare the 3D void finder with 2D void finder, and they look very different. And I just want to say that, so in the next few slides, I'm showing quite a lot of plots, but I just use the same layout for the different void finders, just compare. For this particular case, this is the so-called troughs, which was used in the DES paper, I think. You can see there's a lot of overlapping between the different troughs, different voids. And in this case, you can expect that there's a lot of correlation in the errors. So basically, this is the correlation matrix of the different void finders. You can see that in this case, there's a strong correlation. This means that if you want to do error analysis, you need to take into these correlations into account to get a reliable result. So the first void statistic I want to talk about is the abundance of voids. And this is particularly interesting because many modified gravity models have predicted that voids could be larger and emptier. And this void abundance is basically like the abundance of galaxy clusters. And this is a one-point statistic that can be used to quantify your model. Most of the previous studies used void abundance for voids identified from the dark matter field or the dark matter halo field. And conclusions vary, but some of these studies claim that they found big difference between modified gravity and GR. Here we want to say what happens if we want to use the same galaxy field to find voids. And also there's also concern that void abundance is too sensitive to the void finder that is being used, as we have seen in the previous plot. And this may make void abundance not a good indicator for different models. So the abundance of voids for the different void finders is shown in these 6 panels, or 5, because for troughs, void abundance is not well defined, so it is not shown here. Basically, this plot shows the number density of voids as a function of the size of the voids. And you can see that you have fewer large voids and you have more small voids. But you can also see that among the different models, there's a huge variation of the void abundance. In this case, here, the peak is below 10 to the 4, while in this case, it is well above 10 to the 5. So the different void finders do give you very different predictions of void abundance. However, if you compare the different models for the same void finder, any of these void finders, for example, this one, you can see that generally they agree very well. By the way, these different color lines will be used for the next few plots. GR is black, F6 is orange, and F5 is green. And the dashed line is redshift 0.5, and the solid line is redshift 0. You can see that within error bars, the void abundance in different models all agree for any of the void finders used. So this is because we have specifically tuned the galaxy catalog so that they have the same number density and the same galaxy clustering in different models. And this buries any effect you would see from the void abundance. So the conclusion from here is that void abundance is not a good discriminator of models. Now we want to look at the radial distribution of galaxies inside voids. So what is plotted here is the number density of galaxies as a function of the radius from the void center. And again, these different void finders display quite different results. There's a common feature, which is that inside the void, which is this region, there is almost no galaxy, or very few galaxies. This is as expected, because they are voids. And near the void boundary, there's a sharp peak of the void number, of the galaxy number density. While if you go to farther away from the void center, then you go back to the background value. So again, if you compare the different models within the same void finder, you will see that their relative difference, as shown in the lower panel, is very small. This is again because the galaxy field has been tuned to match the galaxy clustering. Once that galaxy field is fixed, you really don't have any freedom to find the difference between the number density profile of void. And this is no longer a good discriminator of models either. Now what happens if we want to look at not the galaxy number density profile, but the dark matter density profile? And the plot is shown here. So you see some similar feature as the galaxy number density profiles. Again, inside the void, there's little dark matter. At the edge of void, you find a sharp peak. And then if you go to further away from the void center, the density goes to the background density. And again, these different void finders display different results quantitatively. But if you look at the relative difference between models, for example, this model, you can see that actually, although we have tuned the IPhT catalog so that the galaxy number density voids are the same in different models, the dark matter density profile is different. And this is a real difference between the different models. This is not affected by the tuning of the IPhT. So this means that if we can somehow measure the void dark matter density profile, then that can be a good discriminator of the models. So, of course, we know that the dark matter density profile of voids can be measured using the so-called weak lensing, which was discussed several times this morning. And in this case, we just focus one specific statistic, which is the weak lensing tangential shear profile of voids. And this is defined as the ratio between these two quantities, delta sigma, which is the difference between sigma r, which is the projected surface mass density at radius r from the void center, and this quantity, which is the mean projected surface mass density within radius r. And the denominator sigma c is a combination of the distances between the source and the length. So this plot now shows the predictions of the void lensing profiles in the different models for the different void finders. Now, interestingly, we see that similar to the case of dark matter density profile, the different models do show a difference. For example, here you can see that there's a peak in the difference between the models at about void radius, and this is because of this sharp transition feature. And this difference is particularly prominent for the cases of 2D voids, in which case the difference you can see is much larger than the 3D voids. And also the error bars here are much larger in the 3D voids than in the 2D voids, which is barely visible here. These error bars are statistical error bars. So this shows that void lensing could be a good probe to test apart the different models. But the performance does vary across the different void finders. So what we want here to do is to do a forecast of the possibility of using surveys like Eucild and LSST to test gravity with voids. And for the forecast, we assume a Eucild-like survey that covers 20,000 square degree with a source number density of a galaxy equal to 30 per arc minutes, and the median redshift of the source is 0.8. And another is a SST-like survey with 18,000 square degrees that has a number density of source galaxy which is equal to 40 per arc minute, and the median redshift of this survey is 1.2. And the voids are assumed to be distributed uniformly between redshift 0.3 and redshift 0.7. So to quantify the difference between the different models from GR, we use this called signal to noise, which is defined by this, where delta gamma Ti and delta gamma Tj are the differences in the tangential shear profiles for the I spin and J spin between the different models. And this is the covariance matrix between the different bins. So the result is shown here. And this plot shows the signal to noise for the F5 model, and this is the signal to noise for the F6 model. And the different colors are for different void finders. The dashed line is LSST result, and the solid line is Eucild. So one interesting feature is that we can see, as expected, the 3D void finders all give quite low signal to noise. And this is because the error bars for those void finders are too big. While surprisingly, the 2D voids give much higher signal to noise. And it is of order 10 or more for F5 model, and somewhere between 1 and 10 for the F6 model. So this shows that if we can beat down the systematic errors of these surveys to at least below the statistical errors used in this analysis, then there's a real possibility that these surveys can be used to test apart the different models of modified gravity. Finally, I want to ask more generally, what about other models? So this study is about FFR model only, and we know that FFR model is a representative example that can capture the behavior of several different classes of models. So at least those predictions could be qualitatively applied to those families of models. But this will not apply to the Weinstein type of models, such as DGP and cubic Galilean. Cubic Galilean is different, such as DGP. And so I'm not showing the result here, but preliminary study shows that for Weingart screenings, the performance, the relative performance of different void finders is just the opposite, with 3D voids outperforming 2D voids. And finally, for models like Galileans, photon geodesics can be affected by modified gravity. So there's a much stronger weak lensing signal of voids in these models, which is, this shows an example. So the red line is the lensing signal for no modification of gravity. And the green and blue lines are void lensing profiles predicted by cubic Galilean model. And you can see that this is not just a few % difference. This is a factor of 2 difference. So this is too big to be compatible with observations. So summary of the first part of my talk is that future galaxy surveys offer good opportunities to test gravity using voids. And here we compare the different void finders for testing FFR type of gravities. And we found that 3D voids are better than 2D voids. Basically, that's the news. I'll move to the second part of the talk. So this is a side project that was done by me and a former student of mine at Portsmouth. And it is about the standardizability of type 1a supernovae in the context of modified gravity. So this is a short talk, so that I skip the overview. Just jump to the context and the motivation. So the motivation here is twofold. On one hand, we know that cosmic acceleration is a big problem in cosmology. And although that we have many nice ideas being proposed here, I dare say that currently there's no completely satisfactory solution to the cosmological constant problem. On the other hand, with the data quality being improved in recent years, people have discovered various discordances and discrepancies between different data sets. So these are tensions that have been confusing. So there have been efforts to explain these tensions either by claiming that they are due to observational systematics, or they can be due to missing new physics. So here I want to ask the question whether it is possible that some of the tensions or even some of the observations can be a misinterpretation of data due to missing some piece of new physics. So I'm talking about supernovas. So I want to say a few words about type 1a supernova, of which the widely accepted model is that a white dwarf accretes materials and goes beyond 200-second mass, so that it collapses gravitationally. And this raises the temperature and the pressure at the core of the white dwarf, so that it triggers a runaway carbon-oxygen thermonuclear fusion, which leads to a production of a large amount of radioactive nickel-56. And this nickel-56 will then decay to copper-56 and iron-56. During this, it produces radiation that powers the light curve of the supernova. So supernovas are considered to be standard candles in cosmology. But they are not. They are standardizable candles. What practically this means is that if you have a population of supernova and look at the light curves, they display a range of behaviors such as shown here. So you see that there's a pattern in these supernova light curves, with the lower ones also being the narrower ones. In practice, you can do a standardization of the supernova light curve, or what I call a rescaling. What you do is that you can, for example, choose one supernova light curve as a template and stretch the other light curves by some factor so that it matches the width of the template. And then you multiply the height of the light curve by the same factor. And by doing that, you get a good agreement of the different light curves of the supernovae. So this is how you standardize the supernova light curves, in standard gravity at least. Now, there are different ways to predict the supernova light curve, and a more accurate way is to use a full simulation, but that is too expensive. So here I'm using a semi-analytical model, which is described by this equation. So this equation is telling you that, hi, I'm here. I can explain the supernova light curve, but please don't look into details of me now. So this model has, after some simplification, it has 6 parameters. So these 6 panels show the effects of varying these 6 parameters of this model. And the 3 red parameters are not being the radius of the initial supernova ejecta, those C being the central density of the supernova ejecta, and FCO is the mass fraction of unburned carbon oxygen inside the white dwarf progenitor, so inside the ejecta. And the effects of varying them are shown here. So you can see that the effects are particularly small. And for this study, we fixed these parameters to be some typical value. And in the case of the radius of the initial supernova ejecta, we just choose it to be the same as the radius of the progenitor white dwarf. Well, these blue parameters, 3 blue parameters, varying them has a big effect on the supernova light curve. So on the top right panel, I'm showing the effect of varying the mass of the supernova ejecta. In this study, we assume that the mass of the supernova ejecta is equal to the mass of the white dwarf progenitor, which in standard gravity is 1.44 solar mass, the Chandrasekhar mass. This plot shows the effect of varying the mass of Nico 56 in the supernova ejecta. So, for example, this top curve here shows the case, extreme case, where all of the mass of the supernova ejecta is in Nico 56. You can see that it produces a large amount of energy, which is why the light curve is both higher and wider. The bottom panel shows the effect of varying the kappa parameter, which is the effective opacity of the supernova ejecta. So this opacity determines how easy radiation produced by the supernova explosion can escape the supernova ejecta and be observed by us. For example, this blue line is the smallest value of kappa, which means this is the least opaque case. In this case, the supernova light curve is higher and narrower. This is because for this less opaque case, radiation trapped in the ejecta could be easily escaping from it. Now, not all of these 6 parameters are independent of each other. Some of them are actually interrelated with each other. One good example is these last 2 parameters, the mass of Nico in the supernova ejecta and the effective opacity. So there's an explanation to why they are correlated. But to cut a long story short, the argument is that if you have more Nico, then you get more energy and more heating. So you get an ejecta which is more ionized. And then this makes the ejecta less transparent to radiation. So it has a higher kappa value. So in principle, this relationship between the opacity and the Nico mass can be calculated from first principle. But in this study, we have chosen a phenomenological way to fix the relationship by requiring that after the rescaling or after the standardization procedure, all of the supernova light curves agree with a template light curve. So practically what we do is this. We have a range of supernova light curves. These dashed lines, they have different mass of Nico. And then for each of them, we find the red kappa value that makes them rescale to the common template. And after rescaling, you see that they agree well with each other. These are the solid lines. And then we get this relationship between Nico mass and effective opacity. We assume this relation to be independent of gravity, which is a fair approximation because this is determined solely by nuclear physics and atomic physics. Now, if we have a modified gravity, say the simplest case with a time variation of the gravitational constant, then we know that the Chandrasekhar mass will depend on G in this way. And we assume that the ejector mass is equal to this chandrasekhar mass. So the ejector mass also depends on G. There are other minor effects of varying gravity, but those are small effects. So what we do is that now we choose different values of G. Say, for example, we have a G that is not equal to G naught. G naught is G value today. But we have a G that is 1.1 times today's value. And we used light curve model to predict these different dashed lines. These are the different light curves for cases with different nickel masses. And then we do the same standardization or same rescaling procedure using the already derived nickel mass and the opacity relationship. Surprisingly, we found that after the rescaling, all these light curves still agree with each other. And these are the solid lines. So this means that even with different gravitational strings, supernovae are standardizable still. However, this black dotted line is where these curves should be in a standard gravity. And you can see that in the case of a stronger gravity, after rescaling, these supernova light curves have a higher luminosity. So this means that if you have a stronger gravity, then intrinsically, supernova will be more luminous. And similarly, this case shows a weaker gravity in which supernova is less luminous. So this implies that if you go to higher redshift, and if you assume that G was smaller in the past, then perhaps at least some of the dimming of distant supernovae could be explained by this weakening gravity. So here we show, the last two slides, we show two examples. The first example is in which G is a function of redshift in this way. And so this plot shows the luminosity distance as a function of redshift. And the top curve here shows the standard model prediction with a lambda CDM, omega m equals 0.3, omega lambda equals 0.7. So this is the luminosity distance redshift relation for that model. Now, if we assume that G actually decays with redshift, then we get this blue line, which is here. It is red below the red line. So this shows that luminosity distance is smaller in this case. This is because in this case, supernovae are intrinsically less luminous in the past, so you don't need as much acceleration as in the standard model. Now if you fit this DL by assuming G is constant, then you get a different best fit cosmology. Now this is the red line, which is very good fit, almost indistinguishable from the blue line. And for this model, you find that G equals constant and omega m equals 0.6, omega lambda equals 0.4. So this means that if you don't properly account for the time variation of G, then the best fit cosmological parameters could be different. And in this case, actually, the omega lambda is smaller, it's 0.4. So now we want to ask, what happens if we are more aggressive and make G change more with redshift? Does that reduce omega lambda further? And the answer is yes. If we have a G that depends on the look-back time in this way, almost linear dependence, then you can show that the linear evolution of G can completely explain the dimming of distant supernovae, and there's no need for lambda. That's my talk. Thank you very much.
Only two of the questions.
I guess my question is shared by many people. There are many evidence for lambda, not only supernova.
Yeah, absolutely.
So what do you have to say about this? Can your model explain them, or?
No. This is an extreme case. I'm not claiming that.
No, but even any case. I mean, the bounds on omega lambda.
Yes.
In fact, nowadays, supernova is not the strongest one, as far as I know. So.
So there were a few things. So one thing, this work basically wants to bring up the point that this is a possibility that may ease some of the tensions between the existing data sets. And whether it does that remains to be checked. So this is one thing. Another thing is that relating to the evidence of lambda, I think there was a recent work by by Alan Blanchard, which claims that if you only look at low redshift probes, excluding supernova, then a model with no lambda can fit the data as well. And there are also other studies which basically says that CMB alone may not rule out a CDM universe and so on. So what I want to say is here is that maybe it's worthwhile to look at the possibility that there's no lambda, and maybe the modified gravity effect can explain the ISW effect and can explain BAO and so on.
Sorry, I mean, here you're assuming, of course, the time dependency of G somehow with redshift, but I mean, it's another scenario, not scenario, but I mean, maybe something that one can do with modified gravity also. Just locally, when you have the supernovae, the explosion, just forget about the cosmological evolution, but just for that, if you have modified gravity fifth force with the screening and all that, that should also change the light curve somehow, right?
Yeah.
So, I mean, has that been also studied or not? I mean, do you have any ideas on what would happen?
No, this is a very, very conceptual, very proof of concept study. And we have not taken into account any more advanced model of modified gravity and local universe.
Okay, that's good.
So I wanted to go back to Diego's point because I didn't understand really your answer. I mean, it's even if there is a supernova, like if we don't believe supernova, there is any way just with CMB and CMB lensing, there's like I think now maybe 25 sigma evidence that you need cosmic acceleration.
Yeah.
So in which one you do not believe, CMB lensing or CMB? Or how is this going to affect?
No, I don't disbelieve any of this. I'm not an expert of observations. I think they have done great work and they should be trusted. What I'm saying here is that, okay, so I'm not trying to suggest that there's no lambda. I just want to say this is an extreme example that if you have varying G, you can explain the dimming of supernova in the past. Another thing is that if you have a modified gravity theories, I don't know, maybe someone can design a theory that can explain CMB lensing, CMB without lambda. That remains to be seen.
Yeah, but if you have a G that varies in time, you need a scalar field also that varies in space.
Maybe, yeah.
And no, I mean for sure.
Maybe not a scalar field. I don't know.
Well, I think you also need the space dependence, and I don't understand how
that
this
could be, but
can fit anything.
The space dependence can be weak, and that may be screening in late times. I don't know. That's why I say maybe someone can design a theory.
Okay, I'm sorry we don't have time because that's thanks for your review.
Thank you.